A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Corn, this whole show runs on GPU compute, and we wouldn't be here without Modal.
Seriously. And that's what powers all our text-to-speech. Everything you're hearing right now.
They're an AI infrastructure platform. Developers use them to run GPU workloads in the cloud with zero infrastructure headaches.
If you're building anything with AI, check them out. Modal.com. If you were to walk into a data center today and crack open a quantum computer, you would be in for a massive shock. You wouldn't find a single CPU, no green sticks of RAM, no spinning fans, and certainly no traditional motherboard. Instead, what you'd see looks more like a gold-plated chandelier or a complex steampunk sculpture suspended inside a giant white thermos the size of a refrigerator.
It is a total departure from the von Neumann architecture we have lived with for 70 years. I am Herman Palpleberry, and today's prompt from Daniel is actually a perfect reality check for the quantum hype. He wants us to look past the algorithms and the spooky action at a distance to ask, what is actually inside the box? Because with IBM's 1121 qubit Condor processor and Google's Willow chip now sitting in racks that you can access via the cloud, the physical engineering is finally catching up to the theory.
By the way, if you think the script for this deep dive sounds particularly sharp today, it is because Google Gemini 3 Flash is powering our discussion. We are keeping it in the family. But Herman, when people talk about quantum computers, they often use classical metaphors. They call the quantum chip a processor, but it doesn't process instructions in a linear way, does it? It doesn't have a program counter or a stack.
Not in any sense we would recognize. In a classical computer, you have transistors that are essentially tiny switches. In a quantum system, the fundamental unit is the qubit, and the hardware required to maintain a qubit is what dictates the entire design of the machine. The reason the hardware looks like a chandelier is because qubits are incredibly fragile. Any thermal noise, any stray electromagnetic radiation, or even a slight vibration can cause decoherence, which is when the quantum state collapses and your data is lost.
So the chandelier isn't just for show. That is the cooling and wiring infrastructure. But let's start at the very bottom of that chandelier. That is where the actual quantum chip sits, right? If there is no CPU, what is that piece of silicon actually doing?
Well, it depends on which type of quantum computer you are looking at. If we look at the systems from IBM or Google, they use superconducting qubits. These are fabricated on silicon or sapphire wafers using standard lithography techniques, which is why they look like traditional chips at a glance. But instead of transistors, they use something called a Josephson junction. It is a sandwich of two superconductors with a thin insulating barrier in between. This creates a nonlinear inductor that allows us to isolate two energy levels to act as our 0 and 1.
Okay, so it is a circuit, but it is a circuit that behaves like an atom. But IBM and Google aren't the only ones in the game. I keep hearing about trapped ions and photonics. Do those even use chips?
That is where it gets wild. In a trapped ion system, like what IonQ or Quantinuum builds, there is no solid-state processor in the traditional sense. The qubits are individual atoms, usually ytterbium or barium ions. They use electromagnetic fields to suspend these ions in a vacuum, literally holding them in midair inside a specialized trap. To perform a calculation, you hit those specific atoms with laser pulses to change their energy states or entangle them with their neighbors.
That is incredible. So in one version, your hardware is a superconducting loop on a wafer, and in the other, your hardware is a single atom hovering in a vacuum. I imagine the engineering trade-offs there are massive. If I'm a developer, do I care which one is under the hood?
You absolutely do, because they have different performance profiles. Superconducting qubits are very fast. You can run thousands of operations per second, but they have short coherence times. They forget their quantum state very quickly. Trapped ions are the opposite. They are much slower to operate, but they can hold their state for minutes. It is the difference between a sprinter who gets tired in 10 seconds and a marathon runner who moves at a walking pace.
And then you have the dark horse, which is photonics. Psi-quantum is the big name there. They are trying to use light photons as the qubits. The advantage there is that you don't need a giant refrigerator, right? It doesn't care if it is room temperature.
Theoretically, yes. Photonic qubits can operate at room temperature, which would solve the massive cooling problem. But the trade-off there is that photons don't like to interact with each other. To get two photons to talk to each other for a logic gate, you need incredibly complex optical waveguides and beam splitters. It is a massive networking challenge rather than a cooling challenge.
So we have these different flavors of qubits. But regardless of the type, you mentioned that these things are fragile. Let's talk about the big white thermos, the dilution refrigerator. Because if I am running a data center, I am used to crack units and maybe some liquid cooling for my H100s. I am not used to temperatures colder than outer space.
The cooling requirements for superconducting qubits are truly extreme. Deep space is about 2.7 Kelvin. These quantum chips need to be at 10 to 15 millikelvin. That is roughly 100 times colder than the vacuum of space. The reason is simple physics. At room temperature, atoms are bouncing around with enough thermal energy to knock a qubit out of its state. You have to suck almost every bit of kinetic energy out of the environment just so the qubit can exist for a few microseconds.
And that is why the chandelier has those distinct stages, right? It is like a Russian nesting doll of cold.
You have the outer vacuum shield at room temperature, then stages at 50 Kelvin, 4 Kelvin, and then finally down to the mixing chamber at the very bottom. Each stage uses different isotopes of helium, specifically helium-3 and helium-4, to leach away heat through a process called spontaneous mixing. It is a closed-loop system, but it is incredibly power-intensive and takes days to cool down, from room temperature to operational levels. You can't just flip a switch and start computing.
I love the mental image of a sysadmin waiting 3 days for the server to cool down before they can run a cron job. But here is what bugs me. If the chip is at the bottom of this deep freeze, and the control electronics are outside at room temperature, how do they talk to each other? You can't just run a USB cable into a dilution refrigerator.
This is actually one of the biggest bottlenecks in quantum hardware right now, the cabling. If you look at a picture of the IBM Condor, you will see hundreds of blue coaxial cables running down the stages of the refrigerator. These are high-frequency microwave lines. To control a superconducting qubit, you send a precise pulse of microwave radiation down the wire. The frequency, phase, and duration of that pulse determine whether you are doing a bit flip, a phase shift, or an entanglement operation.
So the software we write is actually being translated into microwave pulses. That sounds less like programming and more like being a radio station operator.
It is very much like that. When you write a circuit in a language like Qiskit or Circ, a compiler breaks that down into gates. Those gates are then mapped to specific microwave pulse sequences. Those pulses have to be timed with nanosecond precision. If the pulse is off by a tiny fraction, the gate fails. And because those cables bring heat down with them, you have to use specialized materials like niobium titanium that don't conduct heat well but do conduct electricity.
This is where I start to see why we don't have these in our pockets. You have a massive fridge, a forest of coaxial cables, and then outside the fridge you must have a massive rack of classical electronics just to generate those pulses.
You hit on the most important point that most people miss. A quantum computer cannot function without a high-performance classical computer sitting right next to it. We call this the control stack. You need field programmable gate arrays and high-speed digital to analog converters to generate those microwave signals. And once the quantum calculation is done, you need classical hardware to read the result, which involves measuring a tiny shift in a resonator signal and turning that back into a 0 or a 1.
So the quantum computer is more like a specialized coprocessor. It is like a GPU on steroids, but for very specific math problems. It is not replacing the CPU, it is being babysat by one.
It is a hybrid system. In fact, for things like variational quantum eigensolvers, which people use for chemistry simulations, the calculation bounces back and forth between the CPU and the QPU, the quantum processing unit, thousands of times. The CPU handles the optimization, and the QPU handles the complex state simulation. If you don't have a low latency connection between your classical server and your quantum fridge, the whole thing grinds to a halt.
That makes a lot of sense. Now, let's address the elephant in the room, RAM. In my PC, I have 64 gigabytes of DDR5 where I store my browser tabs in my operating system. Where does a quantum computer store its intermediate data? Is there quantum RAM?
As of March 26, 26, the answer is effectively no. We don't have a way to store a quantum state for long periods and then retrieve it later like we do with classical memory. In a quantum computer, the qubits are the registers and the memory all at once. You load your data into the qubits, you perform your gates, and then you measure them immediately. Once you measure them, the quantum state is destroyed. It collapses into classical bits.
That sounds like a nightmare for any complex algorithm. It is like having a calculator where the screen turns off and wipes the memory the second you look at it.
That is exactly the challenge. There is research into quantum random access memory, or QRAM, which would use acoustic waves or specialized optical traps to store quantum information, but we are nowhere near having a commercial version. Right now, every quantum program has to be short, enough to finish before the qubits naturally decohere. This is why coherence time is the most cited metric in the industry. If your qubits last for 100 microseconds, your hardware better be able to finish those gates in 10.
This really reframes the whole quantum supremacy or quantum advantage debate. It is not just about having more qubits, it is about the physical endurance of the hardware. Speaking of more qubits, Daniel's prompt mentioned the scaling. IBM has the Condor chip with over 1100 qubits. Google just announced the Willow chip. How are they fitting more qubits onto the chip if they are already struggling with the cabling? You can't just keep adding blue cables until the fridge is full.
You can't. That is what the industry calls the wiring bottleneck. If you have 1,000 qubits and each one needs 2 or 3 coaxial cables, you eventually run out of space in the refrigerator. The heat load from the cables alone would melt the system. This is why the latest hardware from Google and IBM is moving toward cryo-CMOS. They are trying to build the control electronics, the classical chips that generate the pulses and put them inside the fridge at the 4 Kelvin stage.
Oh, that is clever. So instead of running 1,000 cables from the outside, you run 1 or 2 fiber optic lines into the fridge, and then a classical chip inside the fridge distributes the signals to the qubits.
Precisely. But then you have a new problem. Classical chips produce heat. If you put a chip inside a dilution refrigerator, you have to be incredibly careful that its waste heat doesn't warm up the qubits. It is a delicate balancing act of thermodynamics. Google's Willow chip, which they announced in late 24, actually showed some massive strides in error correction by integrating these control systems more tightly. They proved that, as you add more qubits, you can actually lower the total error rate if your hardware is designed for error correction from the ground up.
You mentioned error correction, and I think that is a huge hardware hurdle. In a classical computer, if a bit flips from a 0 to a 1 because of a cosmic ray, we have ECC memory that can fix it. But you can't copy a qubit because of the no-cloning theorem in physics. So how does the hardware handle mistakes?
This is where the physical qubit versus logical qubit distinction comes in. Because qubits are so noisy, we can't trust just one. Instead, we take a group of, say, 100 physical qubits and link them together to act as one single, perfect, logical qubit. The hardware has to constantly perform parity checks to see if any of the physical qubits have drifted. This requires a massive amount of classical processing power happening in real time.
So when IBM says they have 1,000 qubit chip, they might only have 10 or 20 useful qubits for a real-world program once you account for the overhead of error correction.
On a good day, yeah. Some estimates suggest we might need 1,000 physical qubits for every one logical qubit. If you want to run Shor's algorithm to break RSA encryption, you might need millions of physical qubits. That is why the hardware looks so ridiculous right now. We are in the vacuum tube era of quantum computing. We are building these massive room-sized machines to do what a pocket calculator will eventually do.
It's funny you mentioned the vacuum tube era. I was thinking about the transition from vacuum tubes to transistors. Do you think we'll ever see a solid-state revolution for quantum hardware where we get rid of the dilution refrigerators?
There are people working on it. Nitrogen vacancy centers in diamonds are one approach. You essentially use a defect in a diamond lattice as a qubit. Those can operate at room temperature. The problem is scaling them and getting them to talk to each other over long distances. Then there is topological qubits, which Microsoft has been betting on. These are theoretically much more stable and wouldn't need as much error correction, but they are incredibly hard to create. We are still trying to prove they even exist in a stable form.
So, for the foreseeable future, if you want to do quantum computing, you are going to be renting time on a giant gold chandelier in a basement in New York or California. Which brings us to the practical side of this. If I am an engineer or a dev, I am not going to be buying one of these for the office. I am using a cloud API. How does that change the way we think about the hardware?
It means the hardware is abstracted away, but you still have to be hardware aware. When you submit a job to IBM Quantum or Amazon Breakit, you aren't just sending code, you are sending a transpiled circuit. The compiler has to know exactly which qubits on the physical chip are connected to which other qubits. If you want to entangle qubit A and qubit B, but they aren't neighbors on the chip, the hardware has to perform a series of swap gates to move the data across the chip.
And every swap gate adds noise. So if you write inefficient code that moves data around too much, your final answer is just going to be random noise.
It's like having a CPU where moving data from register A to register B has a 5% chance of corrupting the data. You would write your code very differently. You would try to keep everything as local as possible. That is the stage we are at. We are writing code for specific physical layouts of chips. We haven't reached the era of write once, run anywhere for quantum.
It's a bit like the early days of assembly language, where you had to know the specific register layout of the processor you were targeting. It's a very raw form of computing. Herman, you mentioned that these machines are specialized accelerators. We've talked about what they can't do. No RAM, no general-purpose OS. But what is it about this weird hardware? The microwave pulses and the superconducting loops that actually makes them faster for certain things. Is it just that they are doing everything at once?
That is the common misconception, the parallelism myth. It is not that it tries every answer at once. It is that the hardware allows for interference. Think of it like noise-canceling headphones. The quantum gates are designed so that the wrong answers destructively interfere and cancel each other out, while the right answer constructively interferes and gets amplified. The physical hardware is essentially a giant interference machine. We are using microwave pulses to tune the waves of probability so that when we finally measure the qubits, we are highly likely to see the correct solution.
That is a much better way to think about it. It is an analog process that yields a digital result. It is almost like a very high-tech version of those old slide rules, but using the fundamental laws of the universe instead of wooden slats.
That is a great way to put it. And because it is so fundamentally different, the bottlenecks are different. In a classical computer, the bottleneck is often the memory wall, the speed at which data moves between the CPU and RAM. In a quantum computer, the bottleneck is gate fidelity. It is the precision of those microwave pulses. If your pulse is 99% accurate, you can only run about 100 gates before your result is 50-50 garbage. We are currently fighting for those extra nines of precision, 99.9, 99.99. That is where the real hardware race is.
So, looking at the practical takeaways for someone interested in this. If you are a developer, the inside of the box matters because it dictates your constraints. You have a very limited number of operations you can perform before the environment wins, and your data vanishes.
Right. And my first takeaway would be, don't wait for the hardware to be perfect to start learning. Because the cloud providers, IBM, Google, Amazon, Microsoft, have made this incredibly accessible. You can go to IBM Quantum right now, sign up for a free account, and run a circuit on a real superconducting chip in Poughkeepsie. You will see the noise, you will see the errors, and that is the best way to understand the hardware.
And the second takeaway is to focus on the software-hardware interface, learning how to optimize a circuit for a specific topology, meaning the way the qubits are laid out, is a highly valuable skill. It is the modern version of being a high-performance assembly coder.
And third, keep an eye on the hybrid side of things. The real breakthroughs in the next 5 years aren't going to be quantum-only apps. They're going to be classical applications that offload one specific, impossible math problem to a quantum fridge. Understanding how to manage that data flow between a Linux server and a dilution refrigerator is where the jobs are going to be.
It's a wild world. I still can't get over the fact that we built a thermos that's colder than the void of space just to make some atoms dance. It feels like we're cheating at physics.
In a way, we are. We are forcing nature to stay still long enough to do our chores. But the more we learn about the hardware, the more we realize that quantum computing isn't a replacement for what we have. It is a new tool in the shed. You wouldn't use a chainsaw to butter toast, and you wouldn't use a quantum computer to run a spreadsheet. But if you need to simulate a new catalyst for carbon capture or fold a complex protein, you finally have the right tool.
Well, I'll stick to my classical spreadsheets for now, but I'm glad someone is keeping those chandeliers shiny. This has been a fascinating look under the hood, or under the vacuum shield, I guess.
It's a lot to take in, but that's why we love these props. Thanks to our producer Hilbert Flumingtop for keeping the show running smoothly while we get lost in the subatomic weeds.
And a big thank you to Modal for providing the GPU credits that power our research and the generation of this show. We couldn't do these deep dives without that kind of classical horsepower.
If you enjoyed this dive into the quantum thermos, leave us a review on Apple Podcasts or wherever you listen. It really helps the algorithm find other curious minds.
This has been My Weird Prompts. We'll be back next time with whatever strange topic Daniel throws our way.
See you then.
This episode was produced using Google Gemini 3 Flash, text-to-speech by Chatterbox.
Thanks for listening to our show, My Weird Prompts, where our thoughts go from slow takes to facts on cue. We change and follow through. My Weird Prompts.